Hello, this is my video for Project 2 for Mr. Osby's class, where we're going to be doing a 2D flow, for the airflow on a flat plate. And we're just going to get started, just make it on Fluent, and showcase everything we need to show. This is the test one that I had already done, but for now, let's just open up geometry and just get right started with it. Design modeler. Let's just get right into this and just get it done. This one had a couple more confusing parts than the first project, but it was just because I didn't really know how to work the program well enough, but now I understand where to go and what everything does, so it wasn't that bad. But yeah, I'm just starting off making a sketch, making a rectangle, just to get it all started. Then we can give it some dimensions right now. Go to vertical one, horizontal one, and a vertical dimension. Just like that. Now, if you want it to be 1 meter in length, 100 centimeters, and we're going to make the height, if it would go in, 0.5. Now we can zoom into that. This is our shape, essentially, where everything will take place. This is just our scene that we have. Now we have that done, we can go and make surface from the sketch, apply that sketch that we just made, and generate that. That's done. Whole geometry portion is complete. From there, we can go straight to the mesh. The meshing is, I think, the most important part of this, because you don't want to mess it up. You want to make sure you get it right. So, waiting for that to open, I guess. There we go. And here we are. Okay. Perfect. So mesh. First mesh I want to do is the face mesh. Just of that right there. That's pretty good. And we can generate that face mesh. The mesh for this one is going to look pretty interesting. I kind of liked it. Thought it was cool. Let's give it some sizing meshes and select edge. So we can apply that. Number of divisions. We can do 80, 50. Say no here. And hard behavior. And just like that, we can generate it. Perfect. Now this is what we have. We have two more sizing ones we're going to do now. We have the left and right. Number of divisions. We'll be doing 60 divisions. We put no on the capture. We got hard behavior. But now for this sides, both the sides, we want there to be a bias. And the bias is going to be the very top one, where it's kind of like the concentration of how many meshes you want per thing. And the bias factor would make that 70. So as you can see, it just gets kind of just more concentrated in the meshing as you get down to the bottom, which is what you want, because you're seeing how the plate, which is on the bottom, going to be affected. So all the meshing should be really concentrated on that plate to really see what's happening. But now we can generate that one. And it's going to take on this cool look. And you can see it's really dark right there because that's really, really concentrated with mesh. Now we have to do it to the other side. But then we run into a little thing when we do it on this side. You'll see that now. No. Hard. So when we select bias, not bad. When we select bias, you'll see that it's going up instead of downward towards where the plate is. So you need to select the wall again, and when you go to reverse bias, you apply it, and it just flips it so that it's going down the way it's supposed to be. And now we can generate that. And there we go. Now we can look at our mesh, and this is perfect. Now all we need to do is name our different parts. So I'm just going to name the surface as a whole. You click it, press N. We're just going to call this air or airflow. And then we can go to the top part, back to edge. Now the top, it isn't really a plate or a wall, so we can just call this field pressure. And over here, we know the names for these, the inlet and the outlet. And then at the very bottom, most important one, is the plate. Perfect. Everything's named, as you can see. Plate. Now we've done with that part too. Now for the most important parts, the setup. To really, this is where you get everything, by the way. Like, just all the information you need for the different parts for the project. All of them are done in the setup, essentially. Well, one of them is done for the results page, but majority of it is set up. And now that we have it open, let me see, double precision. Yeah, that's good. We don't have to open these anymore. We can close both of these now. The geometry and the mesh have both been used, and now they're good. We wait for this to open though. Takes a little minute. There we go. I think it's good. Yeah, looks really cool. There we go. Alright, models. First, the viscosity, laminar. First thing we gotta do. Red under models. Now we can get to the more interesting stuff. We go fluids, air, our fluid. The density is 1.2, and this is 1.8 e to the negative 5. Perfect. We change, create, and we close that. Now that's been messed with. We can look at our boundary conditions. Oops, boundary conditions. And we can just check them all. So for the inlet, the velocity does need to be changed, because it should have a velocity of 2 meters per second. Can apply and close that. This doesn't need anything done to it. It should just be fine. Outlet is fine. The plate should be stationary. So we check this. Yeah, just stationary. It's not moving. And the field pressure should be fine too. Now that we've done that, we can keep going down. We have methods, controls. I think we are good to just run it, I think. With everything that it has the velocity. And we just open this. Set it to a couple iterations so we have a lot. And let's just do that so we can initialize and calculate. I did need to do one more thing. Where is this? The residuals right here under monitors. I just want to change that to be a little more just so it's a little more specific. So it takes a little longer to converge. That's why I have so many iterations. So let me just do that. Let me initialize and calculate again. And now wait for this one. It'll take a little longer to converge for this. Because before it stopped at the -3. And now we're waiting for all of them to at least have reached e to the 6. So -6. And now they all have. So it just took a little longer. A couple more iterations of it. But it's reached. And now that we have that, we can go and set up the vectors. Now the vectors here. We want to see the vectors that are happening at the plate, the velocity vectors happening at the plate. We can see all of them, yeah. And then we can zoom into the plate stuff. So so the plate would be right here. This is the plate. And that's why all these speeds are so slow here, because the plate is going, but it just shows how it would move right above the plate. And then we can show also the pressure contours of it. So contours, the pressure, static pressure, and we can save and display that. And then we can also just see the pressure contours that are happening at the bottom. So the first part of the project, just to show what's happening at the plate. Now we can get to the graphs. So we can go over to results, open that up. And we'll leave this open because we will be going back to that to showcase the other stuff like the wall shear and the skin friction. Set that there. Perfect. First thing I'm going to do really quick is just make the lines so we don't have to think about them. And this one will be x equals 35. X 35. We'll just set out that. Now the point, it's in meters, so 0.35 meters. And the height of this was 0.5. We do 100 samples, and we can apply it so we can get our first line. Make another line, x75. And do the same thing, but now we move it to 0.75. Put the height there, 100 samples, and we can apply that. We have both lines now. Let's start off with the chart. Here in the chart is the velocity. Profiles. Perfect. Let's set the data series 35. We can call this x equals 35 centimeters. And then we go to the next one. And we pick x75. And we call that one x equals 75 centimeters. Perfect. And now for the x-axis, we want the velocity. And the y, we want the y. And everything should be good, and we can apply it. And we get this weird goofy graph, but what we really want to go to, it's really pointy too. Just saw that. Maybe what I should do really quick is make this 1,000 samples. And then go back to the chart and apply it again. And it's just so it gets a little more rounded. It was very pointy. And I kind of just want to zoom in on what's happening there. So I'm just going to change the ranges so we can kind of just look at it and not have to meander around it. Let's do 0.8. And the max we do 2.3. And for the y-axis, we can also change that. We can go from 0 to 0.1, just so we can kind of zoom it in. There we go. That's a much better picture of what we're supposed to be seeing. But that looks pretty good. That's for the x. And now the boundary layer thickness would just be these points right here, measured downward. The very end for both of them, which you can just get right now by looking at it in the graph. You can zoom it in even more, make it easier to read where it is, where each point is. Just kind of really center on it. But that's just that part. Now for the next part, to get the wall shear and the skin friction, we need to make some XY plots in this one. That's where I found it to be the easiest to do. You just make the y-axis wall fluxes, and right here, wall shear stress. I'm going to make it x wall shear stress, because it's the one that's going, along the plate. It's on the x-axis. And we're going to save. Now, to make the so we could, like, what's the word for it? Compare with the theoretical ones. I made it into a file, and I used that file in an Excel, which I'll show you over here, to make this, so that I could, really compare them analytically through just numbers and graphs. The blue one being the one from you get from Fluent, which you'll see now, and the theoretical one being the one you get from theoretically, just plugging it into the equations yourself and just getting the theoretical answers that it should be. So and you also just select plate, sorry, forgot to say that right here, so you can really just get only the plate. I'm not going to write to a file because I already did that before, but yeah, see, it looks just like that. It is that same line, and the theoretical one will be just like that. Now, sorry, opening a lot of things that don't need to be opening. There we go. That's a wall shear one that we can get immediately. Now, for the other one, we open the XY plot again, we select wall fluxes, and now right under there you have skin friction coefficient, and you can just do the same thing, select plate and then save and plot and close it, and there's your skin friction one, and I will show you that for this too. There it is with the theoretical one. They look a little different. Mainly the Fluent ones are a little higher up here, but they have the same, the same traces. Like, they do the same thing. All the same trends in between them, with where they're curving, where they're heading. It's very similar, and they're not supposed to be the same. They're supposed to be at least a little off, because the program isn't going to get it exactly right. You'd have to mesh it a lot, I'm assuming, to get it to be exactly like the theoretical one, but it is very close, and it just shows that if you did do it more and more and more, you would get it eventually, right? Okay. Now, for the last one, we need the drag coefficient. So for here, we go not in plots, but reports. So the report here for forces would give you the total drag force that is happening at the plate. I don't know if you guys saw what I did, but I just selected force reports right here, clicked plate, so that it's only looking at the plate, nothing else. And then we just print it out. It'll show up right down here. And this number here, the total number here, that is your total drag force on the plate. And using the equations that you're given, you can then figure out what the number is you're going to get. I already have it done over here. We can go over here. I already did it before. I circled it red. There, I got the total drag force on the plate, calculated the one with Fluent, and then I got the theoretical one. That realistically shows the whole organization of how to get it done and how to find each thing. Then the rest is kind of just math outside of the program, or Excel, because I did have to do Excel to compare them, but it worked out pretty well. And it made a lot of sense, honestly, after I had finished doing all of it. It all made a lot of sense. But yeah, that's my project 2. I hope this did what it needed to do. Goodbye.